I'm taking only 12 credits in the busy semester. I don't know. I feel like there's quite a big difference between number of credits and the actual number of hours you need to credit class or something. Yeah, there's a last. You have the project.
All right, I'm caffeinated. Let's get ready. Let's get going. So we're going to switch off of timers to serial buses for this week and maybe next week. But to get started, we have office hours today. I just saw somebody on Piazza wanted to walk through one of the exam problems. Office hours is a great place for that. It's kind of hard to do it through Piazza. It'd probably give you the level of detail you're looking for. And you can also ask for other office hours, and depending on my schedule that week, I'll see what I can do. You could also ask the IAs, GSIs. However, they didn't make the exam question, and they might be not as familiar, but they also can give you a good shot. Project ideation slides are due tomorrow night at 11 o'clock. And the team formation event is going to be on Friday. Oh, I should put the times on there. What time is it, 4:30? What did I say?
I think it's 4:30 to 6:30.
See, we can make my slides together. I like that.
I love having this cheat.
Great. And then homework 5 has been released. I think this one's shorter than the other ones, and it's due next Monday. Okay. So any logistics questions? Nope.
For the ideation slides, it's 3 ideas.
Correct, 3. You can do more. Go crazy if you want, but each individual has to do 3.
So on Monday we did virtual timers, but the slides are not in there.
They're not?
Yeah.
I thought I just looked. They're not there? Okay. Well, if we get a break today, I'll do it, or I'll do it later. Can somebody else confirm that they're not there?
Yeah.
Since like you got to 10, 11, they're back at the top of the list, not at the bottom.
Oh, that's annoying.
Ooh, stupid numbering conventions. Thank you.
That makes sense.
Ooh, slides. Nobody's ever been so excited about my slides. This is the first class looking for my slides. Okay, any other questions? Yo. What kind of pizza? I don't know. What kind of pizza do you guys want? All right, go put a poll up. Go put it. Somebody put a poll up in Piazza. You can vote for your favorite vendor, which I modify against cost. And then there'll be a variety of pizzas from vegetarian, cheese, and meat for all your needs. And I see we get right to the important questions. Where are we getting the pizza from? Okay, any other questions? Great. All right, so we're going to be talking about serial buses in general, and it's kind of broken into 4 modules. And so this is really primarily, how do we get chips to talk to other chips, or devices to talk, or chips to talk to computers, or whatever it is. This is primarily the function of the section. So we're going to start off with a serial bus overview, kind of architecture, things you have to worry about, and then we'll talk about 3 different protocols that you'll use in your labs or in your projects. For those who are excited, there's some reading you can do. The reference manual is great. You just have to, you're at that point where if you really cared, you could just read that manual and you'll probably understand most of the words now. So you're doing well if you can do that. And then if you want to look at the textbook we recommended, this would be chapter 22. All right, so we're talking about communication buses. So again, I guess I just said this, but this is how are we going to get chips to talk to other things? So how do we get these 2 chips to talk to each other, or this chip to talk through USB to your computer? Here, this is a motherboard, so we're talking about a processor talking to maybe PCI Express cards or to RAM. So what's the mechanism for moving data from one device to another one. So things you should consider that we'll cover here. So what's the wiring methodology? Is this going to be serial or parallel? We already talked about parallel buses in the context of the advanced peripheral bus. Speed, is it bitwise, wordwise? How many words per second are you doing? Timing methodologies, we're going to find that there's protocols. So they're synchronous, meaning that there's a clock, and asynchronous, which means they don't share a clock at all, and you have to figure out, or the devices have to do clock recovery to figure out when to sample the data. Some protocols are just point-to-point, and some protocols allow you to talk to tens or even hundreds of devices on a bus. And so figuring out who's in charge and how that happens is important. So part of that's also arbitration. What's the method for deciding who talks when? And then there's protocols and thinking about like data format, like is there overhead on the protocol, like an address, or is there pieces of information for redundancy? So first let's talk about parallel buses. Very much like the APP bus, data sent in parallel. So this is good for high bandwidth applications. You get multiple wires for address, multiple wires for transmit data, and examples would be PCI Express, at least, or these are the most common ones, for what you would see on a PCB. And so just to be clear, we're talking about like these traces here. This is a bus. And so this would be on the PCB. These are examples of parallel cables that have been ripped apart, and you can actually see there's multiple strands going to all these little connectors. If you had a serial bus, which you'll see in a little bit, you still have multiple strands, it's just not as many. And this is the more typical interface for serial buses or parallel buses today, where you have these edge connectors. So these are gold leaf or gold edge connectors, and the PCB actually mounts inside one of those brackets up there. And that's usually how we connect things now. These are old style cables that nobody really uses anymore. And some of the reasons are it's just hard to send lots of parallel data through wires just for electromagnetic reasons. They interfere with each other. So usually try and keep the traces pretty short and well controlled. How are we doing on parallel buses? Okay. If we get real excited, somebody wants to ask, we can go through parallel buses for Falstad. But in this example, which is linked in the slides, basically you just have a counter here, and we're just a row of 8-bit registers, which is clocking data over. And we have a clock that goes through, and each cycle is going to tell this thing when to latch in. So there's a setup phase where this sets up data, usually like say on the positive edge, and maybe on the negative or the falling edge, it clocks the data in. And that way we can get lots of data through. Okay. The counterexample, which is mostly the study for what we're going to do the next couple of weeks, is a serial interface. So you get a single wire, could be multiple wires, I suppose, but a single data wire that's going to send data 1 bit at a time. And so now, before it was 8 bits go across in parallel. Here, now you have to take more time to send the same amount of data. You take those, instead of doing parallel, you shift 1 at a time if you're going to send over a byte of data. Typically requires some amount of synchronization between the two things. There's ways around that. And usually there's a few extra wires for clock, maybe shaking, those sorts of things. And these are inexpensive ways, in a sense, from a number of pins that you need, a number of wires that you have to use to get data from one device to another device. They're also better for long distance transport. So Ethernet is a serial protocol as opposed to a parallel protocol, because it's much easier to make data go long distances. And examples would be Ethernet, RS-232, which is a UART version. Even here we have I2C, but even optical things like IR data. So like your remotes are considered to be serial, even though the transfer mechanism is IR and not copper. And so this is just examples here. The USB cable, right? They actually have plus and minus data, so they're doing differential data. So because they're worried about noise and other interference, they have opposite versions of the data just so that it's a differential pair. But essentially there's a data line ground line, power line, and then everything else is shielding. And then in this chip scenario, it's very hard to see, but it's not as obvious with serial communication because it's just 2 wires. And in this particular case, they happen to wire those traces underneath the chip, which is kind of frowned upon. It's not illegal, it still works. It's just not the best routing technique, but sometimes you got to do it. And so those come over to these pins. And that's how they're going to connect. This chip is a bridge that goes from whatever your microcontroller wants to talk, so I2C, SPI, something like that, and we'll bridge over to UART, and we'll turn that into USB signals, and we'll send out USB to your computer. So now you can get your microcontroller to talk to your computer. One of the core pieces that's really important to serial communication is this idea of a shift register. So 270, you talked about shift registers? Fantastic. So the key conceptual idea here is a shift register is how you transfer parallel data to serial data and back. It's like this nice little mechanical tool that's going to take whatever it is, could be 32-bit data off the APP bus, and then this is going to serialize it and push it across that, that data line. So maybe we can see that here. So here I set up some data. What do I have to do? Oh, is it clocking out? Nothing's happening. Let's say if I, it's been a while. Maybe I should have tried this before since last year. Nope, try this. Oh, it's just 1101 here. Let's make it a more interesting thing. Stop, reset, reset, stop. All right, now I say go. All right, so here's the clock. Here's the data bus. Why are you not going? Okay, I loaded it in. It's watching a professor struggle here. That's what you're doing. Right, well, how I expected this to work, I think how it's working, is basically 1 bit at a time. It's taking the data and the parallel thing. It's going D1 first, then D, or D0, D1, D2, and over time it's transferring that data over the data bus. But I must have some conceptual problem here. It looks like the data got through here. Okay, so this is a tool that's going to be inside your STM32, which is you're going to take serial data in because the external world is, say, a serial bus, but your microcontroller doesn't talk serial, right? So you could technically just go look at a register, look at your GPIO in register, look at whatever the 0th bit, and then put that in the core, and then every single time, you know, look at that. That would be an inefficient way. It's called bit banging. The better way to do is have a little hardware module, like a peripheral, who is already set up to speak UART or whatever your protocol is, and it just says, oh, I know that 10 bits are coming in, whatever. I'll clock them into a serial or a shift register, and then when the core asks, I'll load it all out in parallel. So that's kind of like the magic trick of shift registers. Okay. Yeah.
The reason why we convert from like series to parallel and then back again.
Is there a reason to? Well, let's say in this example that this is a transmitter, whatever the heck that means, chip 1, chip 2, and I want to send data from here to there. So that's why in this case, oh, and we're assuming that parallel data comes off the APB bus, and we're going to assume that this chip over here is also a chip that works in parallel, right? Like it's got some sort of core in it, and so we're going to send data back and forth. It expects data in parallel. Does that answer your question?
Explain how it works, but didn't explain why.
So why wouldn't we just send it over parallel? What's a reason why, anybody can guess a reason why we choose parallel over serial or serial over parallel?
Space. Space parallel takes up more space.
So we got space on our PCB. Maybe we just don't have room to put an 8-bit parallel bus, but we have room for a wire. What do you think about that?
Yeah, that's a good answer.
Good answer. Any other reasons?
I think in automotive they use CAN bus, which I think is 2 wires, but it's very cheap to have just like way fewer wires in a vehicle. You're saving like a lot of money that way.
Or even like airlines, right? Like airplanes, sorry. You imagine this, the weight of having a parallel bus. You put another pound on that plane over the life of that plane, how much extra fuel does it cost? That's how they measure things. Like this is gonna cost $100,000 worth of fuel. You can't put a coaster on this thing or something. This is like the sort of thinking that they have. All right, so we got space, we've got like space on a PCB, we got space like in our environment, like as we route the cable. What about from a microcontroller pinout point of view? What are we limited in? What version would you rather have, parallel or serial? Yeah. Why?
You wanna don't wanna sorry, words are hard. You wanna use as little pins as possible.
Yeah,
so that you can use
typically.
others.
I mean, there's all sorts of chips that can be made, but typically we're in little small microcontroller land, and demanding that we use 8 of our precious GPIO pins to talk to some other device is usually less desirable, right? It's much easier to say, okay, we only have 32 pins to begin with, let's say, and I'm gonna use 2 of them for UART, and maybe you could talk to end devices with a correct serial protocol, and we'll talk about some of those things later. So now you don't have to have a bus for everything. All right, so hopefully we've motivated some reasons why in the world we'd even want to do this. So what do we said? Things to consider. We'll talk about these a little bit throughout the lectures, but there's some data encoding method, right? Is this most significant first or least significant first? Are there control bits in here? How fast does it go? You know, there's this direct signaling point of view of like how many transitions can you get on this thing versus how much data goes through. We'll talk about that. And then are there methods for detecting errors? That could be either a mechanical method in the sense of extra wires to help with handshaking and control, or maybe just a part of the protocol of you send extra bits to indicate that there's errors. So some things about speed. So serial is pretty good at low speed. You see most of these things are in the kilobytes, 100 kilobytes, some in megabytes. So low speeds are like RS-232, which is equivalent to UART. Things that you'll use are maybe in the medium side are I2C, and SPI is not in here, but that's about the data transfers you can expect. The ones that have been more commercialized, like USB, Ethernet, and FireWire, which I suppose nobody's using anymore, these are getting so fast that you at USB 3, you almost have to think of it as RF waves going through these wires. Right, this is how challenging it's getting to go up to, tens, hundreds of megabytes per second. And that's fine. We're gonna let the fine, engineers really think about how waves propagate through twisted pair down a cable. But just to point out that it is become so challenging, I would not ask some of you in 373 to use USB 3 as a protocol to connect things. We probably always downgrade to USB 1. It makes everything so much easier, and you don't really need the speed right now. Yeah.
Okay, so what does it mean by cheap or expensive connections? Like the component itself?
Yeah, components USB controller is much more expensive than say I2C. So there are costs. Basically, the faster you go, things get a little bit more pricey. Yeah.
Can you explain what you meant by RF waves? So like, it's like normally it's just like high-low voltage, but how does that change in like the high-speed USB 3?
Speeds are getting fast enough that you have to worry about things like impedance. So if you've learned about impedance, it is a bus structure, like a wire structure, requires at high enough speeds that there's a certain ratio between the electric field and magnetic field. And if you're outside that ratio, energy will not transfer easily through this medium. And so you have to create a structure in which the energy will actually flow through. Okay, that was super good. How can I explain this in a different way? When you switch fast, it starts looking like radio waves. And you have to now...
It doesn't look digital, it looks more analog.
Yeah, and it starts behaving more like a radio wave confined in a cable. If you know about coax cable, take some RF engineering classes, it'll be fine. Coax cable is basically a shield with a conductor inside and a media dielectric in between, and it has certain propagation modes in which energy can transfer through. And we find that cables, just wires, start acting like that, we have to start worrying about how they're terminated in the shape of these connections in order to get the data we want through. So for you guys, what did all that mean? When you're trying to go fast, here's the rest of your life, when you're trying to go real fast, at some point things aren't going to work and you call an RF engineer or you call somebody on your team that's done high-speed buses. At some point, digital turns into RF, and it's hard. It gets way harder because now you're working against physics, not just logic of ones and zeros. So know when to call, ask for help. Parallel's like way faster, just in terms of speed, right? And it just kind of makes sense. You're sending basically N serial channels over. That's another way to think about it. So of course, you're just going to be that much faster. And so the industry has gone through and started really where you want to get high speeds is typically they're pushing parallel buses as fast as they can go because you don't need to get serial buses up to like DDR3 speeds. Right? It's just not required. So the optimization for speeds usually in parallel buses where the optimization for long distance is typically in the serial space. Yeah.
One, don't we have DDR5 right now? And two, what does quadruple clock mean?
They have multiple clocks and they clock on different phases.
I thought DD means double. Like, where the quadruple come from?
Look, I stopped making the specs. I don't know. So DDR was double. That was like DDR1, and they keep updating the specs. And you're right, there's DDR5. I just didn't make those slides, but you're welcome, of course, to give me that data. I'll put it in the slide for next year. And then, yeah, there's this. They have more complicated clocking structures, basically. They have 4 clocks to get the data in.
Thank you.
So issues, we talked about some of them. Length, wires. Issues would, think about long cables and you put them next to a power line or something. You guys may remember, I guess it's almost you're aging out of it. GSM, you used to put your GSM phone next to your speakers and you'd hear that sound, right? That's because the shielding on your speaker, there wasn't enough shielding on your speakers, and the RF waves that your phone was sending out, the envelope of those waves was in the audio range. And so basically, your speakers were demodulating that, and now you hear your speakers going off when you're about to get a phone call. And so the way around that is you got to do shielding, and those same concerns about these RF waves that are unintended started influencing your system. That's where we get these ideas of noise coming from. And that's why when we go back to the USB example here, come on. We have 3 shielding mechanisms. There's a foil braid, there's a metal braid that goes around it. There's actually foil around it, and they have an extra ground shield wire, just because they're afraid of external noise getting into this. These wires are pretty big, so now they're the size of antennas, and so they're able to accept energy from outside. So that's why you need to do extra shielding. I think another one on there was capacitance. Imagine you have a capacitor, big capacitor, and you have to drive a lot of current to raise it all the way up to VDD. So you get this RC charge. Any capacitance anywhere means it costs you more energy and more time to raise and lower these voltages. So you want really low capacitance and low inductance traces. RF interference. You also find that like on your little microcontrollers, you want to go really fast with your serial bus. You might all of a sudden find out there's a lot of noise. There's noise everywhere. Your power supply has noise. It's because you're drawing in current. Every clock cycle, every cycle you're sending out data, you draw in a little current, and that causes a little spike to happen on your power supply, and that can propagate everywhere. So just by going fast, you can introduce noise. Probably not a problem for the speed you guys are going, but it can occur if you're trying to take really sensitive measurements. Yeah. All right. Any speed questions? Yeah.
Back when we were talking about parallel buses,
Yeah.
why is more clocks like help the data go faster?
I'd have to go look at that spec. So I believe that it's They're changing, I forget why. I think it's because they want very precise clock edges of when to clock in, and they're trying to make sure the clocks, have you ever seen an eye diagram? It's fine.
Okay, I'll Google it.
I will delete quadruple things until I have a better example for you guys. That's my error. I should never put that on there. But it just helps to tell the thing faster when to put it in. Okay. So timing methodologies. We're pretty familiar with this idea of synchronous buses. Basically here, say we're going to clock data in on the rising edge, and so you want to move your clock transit or your data transitions to like the falling edge so that you meet your setup and hold time. And so here we're going to clock on this edge. You get a 1, a 1, a 0, 0, 1, 0, 1, 0. Pretty nice, makes things easy. If it was very, very fast, or maybe the lines were noisy, these things can skew. Like you might get, they might be delayed because there's the transmission line or the clock trace has a lot of inductance or noise on it, so it might get skewed, and it's possible that they could actually get skewed so that it arrives late. People do a lot of work to make sure that doesn't happen, but there could be some issues. There's other ones where it's completely asynchronous. There is no clock whatsoever, and it's the receiver's job to figure out how are you going to figure out when to clock the data. And this is nice because you only had to have one wire. You always have to have a ground, so these things are misleading. It catches people every year where they're trying to connect like a UART, and they have one chip over here and one chip over here, and no data is going through. It's because you need to have them connected through ground so current can go in a loop. But aside from that, you only need one data line, so that's very convenient. It's just now it's the receiver's responsibility to figure out when to clock data in. And we'll talk about mechanisms for that when we get to UART. So synchronous buses need an extra clock wire, no synchronization overhead. These are usually can be higher speed, and you're tightly controlling the transfer. Asynchronous has most common in parallel buses, and then asynchronous has no clock source. So you don't have to worry about clock skew, but then you have to have this overhead of figuring out when to clock in your data. This is usually most appropriate for loosely coupled systems like external peripherals, like we'll use it in UARTs. Okay. I think we kind of talked about most of these things. Timing methods. Skew. Yeah, flow control handshakes and power consumption. These are actually, should be in a different section, but what I mean by handshaking is oftentimes you need to tell the peripheral and the controller need to agree on when to talk, and they say, okay, it's my turn, and they'll specifically have protocols where it'll raise a line to say it's my turn or not my turn. And flow control is kind of the same, and there's power consumption implications about having a clock. Number of devices. So in the most easiest case, you have a single source, like one point-to-point communication, cheap, easy to do. No need to have those muxes that we had in the APB bus diagrams where you have multiple buses trying to talk back at once. This is just point-to-point communication, easiest. Single to multiple, basically you can have like one controller and multiple targets. Very common, also easy to control. When it gets more challenging is now maybe you have multiple devices that want to have control, and now they have to talk to each other, and they have to agree, hey, I am a controller and I'm a controller as well. They have to agree somehow about when they should talk and not talk, and when the peripherals or the targets they're trying to talk to should talk and not talk. So those are some of the more challenging situations we'll talk about when we get to I²C. This is just a diagram to kind of visualize. So point to point, easiest. The bus one, this is just saying that there's common wires that go to everything. You could also think about this as a star, similar to a star configuration, but everybody can talk to everybody. A star configuration is where you have like one microcontroller with independent lines going to everything. Here, you have one set of lines going to everything. And then a ring topology is where you have one device and it passes a message. If it wants to talk to that device, it has to pass messages all the way through. This is a little getting more rare, but sometimes you'll see it. We won't really talk about mesh or tree structures. although those happen sometimes, less in PCB design. Okay. Arbitration. Oh, these builds didn't go quite right, but you need to figure out when should you talk. So you have multiple devices out on your bus, and you need to decide which one should talk when. And so one way to do it is to have kind of that daisy chain we just showed in that ring topology, where each device gets a turn, device 1, and then it says, okay, your turn, device 2, device 3. More common one for most microcontrollers is the centralized approach, where you have one arbitrator here that's going to talk to each device individually, but you're still going to need some way to say, okay, it's your turn to go. So usually you have more control lines, as we'll see in SPI. And then a distributed one, there's no good image for this one, but this is the idea that you have multiple controllers trying to take control, and there's no particular method, no wired method necessarily of figuring it out. And we'll see some of that in I²C. All right. So popular protocols, UART, I2C, which is, you know what I2C stands for anymore. But it's a kind of a well-established, there's actually a standard for this. There's a standard for UART as well. SPI does not have a formal standard. This is kind of like an informal agreement about data formats in which manufacturers work between. And in the early 2000s, there was lots of disagreement about like polarities in data formats, and that means some chips couldn't work with other chips. Like you get a microcontroller and you're just hoping that the peripheral sensor you want to work with speaks your version of SPI. Now the microcontrollers got advanced enough they can do almost all the different variants. Other ones, Ethernet, infrared, USB, Bluetooth. You know, Bluetooth can be thought about, and all wireless can be thought about as a serial, well, that's not true. Bluetooth can be thought about as a serial protocol. Wi-Fi and other more advanced things do things like QAM, and they actually send multiple bits at a time through different encodings. So it's almost like a parallel bus. Okay, so question for you guys to think about is, do we have any questions? General overview of things you should be worried about and think about when you're choosing bus architectures. Yeah.
So will we be quizzed on like stuff like the network types, like shapes, or like proper protocols, stuff like that?
You might get a question like, these things are set up in this, like given a diagram and said, okay, how do you communicate to device 3? And you would have to have an answer, and you might want to draw upon your knowledge about, oh wait, there's no clock here. I don't see a clock line, or they look in a ring topology, right? So you might have to use some of this knowledge to reason your way about how to approach a problem. Okay. So for you guys, so why does ARM use a parallel bus architecture for the APB and serial bus architectures for chip-to-chip? So I want you to take 30 seconds and figure out and just discuss, come up with an answer why you think they've made this choice.
Because the APB on integrated circuits are a lot less expensive to have parallel buses on than off-chip communication between tiny chips. What it is they buses are like if you want to like switch out the peripheral chips, that is a lot easier with serial than it is
About like a cable.
where my thoughts. I don't know if that's
You just can't do parallel with this.
Much easier to switch out.
I have no idea how to build like parallel is just basically impossible. The standard is technically has multiple data lines, but they just send different things on each data line.
All right, what do we think? Why have they made this decision?
So, number one, they can use less pins because parallel takes a ton more pins than serial.
Okay, so for chip to chip, they've chosen because of pins.
Pins, and also, I'm assuming chip to chip is on the same board, right? Is that what we mean? So you have, instead of having like a million different traces, you can just have like, if it's I squared C, just 2, and then that can go to like the whole, most of other chips.
Yep. So it simplifies, it's not only pin out in that sense, but it also simplifies wiring, if done correctly. So you don't have to have a parallel bus going to this device, another parallel bus going to this device. You can just have one bus for everything. Okay. So why don't they use all the same advantages on inside the chip?
Because if you're inside the chip, then parallel is better because it's faster.
I thought the chip seems small though. Right? Chip seems real small. How are they getting all them traces in there? You're right, it is faster.
Integrated circuits are a lot cheaper.
Well, that's true. The cheaper per like the design feature.
Size.
And it's actually not that big a deal. Like even though you're like, oh my gosh, I have to put like a 32 bus and run it everywhere, you can make the features pretty small. And so you can actually, there is definitely enough room in a chip for very complicated bus structures. The other part is at least the traces, the wires, can go over the digital logic. It's a little bit more rare, but you don't have to have, like, it doesn't rob space for other things. So there's you have more, let's say, PCBs are like usually 2-4 layers, and there's not a lot of room to go into lots of different layers, but integrated circuits sometimes have 7 or 12 layers of metal just for routing, so you get some more freedom in that space. All right, any other reasons or thoughts?
Just a thought is just like, they would have to weigh out, do we really care about the speed of this chip? And if you don't need the maximum speed, or you don't need a certain number, you can afford to just use less wires.
Oh, you mean like internally? Like is it cost trade-off? I mean, I have not seen all the designs, so I don't know when you might use serial instead of parallel. I'm sure there's some reason. Okay, so that's all. That's just a quick lecture to give you a primer on like all the space of serial buses, parallel buses, and now I want to talk about a specific protocol, which is extremely common, which is UART. So this is the Universal Asynchronous Receiver Transmitter. There's reading if you get excited. So what I want to tell you. So this is a particularly old protocol. It was invented in the 60s, late 60s, 50s. And basically it's a method to have 2 wires that talk to each other, and then it got wrapped into a bunch of different standards. So RS-232, RS-422, and 485. There are different mechanical standards as well as different speeds. So a little history, you might remember, well, I don't even know if I had a computer with a RS-232 bus on it, but it used to be particularly common way of just getting data in and out. And they basically, even before that, it was used for computer-to-computer communication. So you used to actually have RS-232 wires going everywhere through a building, like say in the 70s, to send data back and forth. And then they just keep remorphing this technology because they had the hardware, and they're like, well, I'm just going to repurpose it for these other tasks. And it used to be make ring topologies and star topologies and all these sorts of things to get computers to talk to each other. And then technology went forward, right? We no longer have these ports. We have higher data rate, smaller form factor things, but it still works. And the specs is still there. So what you now see is some computing devices have this. Mechanical, like old test equipment still has this. But given that this infrastructure already existed, they generally chose to repurpose it to use it. Yeah, go ahead.
So, for use case, was this used for displays, like for instance monitors?
And that was usually a parallel bus. This was used for like talking to a printer, talking to, even though that was parallel, talking to like this little, like a mouse, those sorts of things. There was a time when this was the primary method to talk back and forth between two computers before anything like Ethernet was around. Anyway, so where I was trying to get to is here. Basically, because we had this standard and technology marched on, we didn't need the standard anymore. But instead of letting it die, the embedded systems people were like, well, wait a second. Instead of going from one computer to another computer across my office, I'll repurpose it just to go from one chip to another chip. Okay? So that's why it still exists today. That's why we're still talking about it. And it's also might be helpful when you go online, be a little careful about the context in which you're looking up documentation. It may be that they're actually talking about things like RS-232, which is how can I describe this? So we'll talk about the data frames and what UART looks like in a second, but basically it's just highs and lows, their start bits and end bits, and it talks about the timing involved, and we'll talk about that in the detail. And the difference between these other two specs is basically they say, here's the voltage that we're going to apply to this communication protocol. So we have data that's going through off, and we're just going to say this is plus or minus 15 volts, or this is plus or minus 16, and for whatever reason this was -7 to +12. They talked about speeds in which it could work at and ranges. So these were all for longer range communications. So this is kind of the history lesson here. This one really got me when I was a graduate student. We had one old piece of equipment in our lab. It was my job when I first got there is get a microcontroller to talk to this thing. And I kept on looking at the bus, and it looked like this. And every data pin, every data piece that I got out of it was inverted. I didn't realize that the spec stated that you inverted the signal when you boosted it up from plus or minus 5 volts to plus or minus negative, or 0 to 5 volts to plus or minus 12 volts. And that's just because they put a big inverter. That was their mechanism of boosting the signal up and making it go across the lab, was putting an inverter there. So it's just important to recognize that there's a protocol on top of a protocol, or a spec on top of a spec. Okay, so back to what we care about today. We've got two devices. They can ride at whatever voltage they want. Usually it's going to be 5 volts or 3.3 volts. Sometimes you see chips that are 1.8 volts. So you will have to consider the voltages involved. Each device has a transmit and a receive. And there's nobody's in charge in this protocol. There's no thing that's the master. There's no thing that's the controller and the initiator. So what you do is you would transmit from one to the receive of the other. So you have to cross these lines. One of the PCBs I made, first PCBs I made, I was like, oh, this is my microcontroller. That's the sensor over here. I forget, maybe it was a display. And I just went TX to TX and RX to RX. Oh, that was a bad news bears. And so I had to take out my little X-Acto knife and cut open the trace and blue wire it in. And then after that, the next board I did, because I didn't know if I was going to get it right, I just put surface mount resistors, and then I could reconfigure them on the fly, so I wouldn't have to cut any traces. These are the things you learn after all your mistakes. But it's really here, it says TX goes into RX, RX goes into TX. You have to keep your naming conventions right. Okay. And there's no clock. We'll talk about how to overcome that clocking issue in a minute. On your Nucleolo device that has a peripheral, and that's why we're talking about, which is the UART peripheral, it's connected to the APB bus. It has a DM interface, DMI, or DA, we didn't talk about DMA, but that's a faster way to transfer data through sometimes. It has interrupts. It also has these shift registers, one for TX, one for RX. And so serial data is going to come in, it gets shifted into parallel, and then you get a buffer here, and then it gets sent out. So now you can go and have an interrupt when your buffer is full. You can go and read out this data as a parallel thing rather than looking at the input pin and pulling it out bit by bit. I think this says all the same stuff. So this is just more of a detailed version of what a UART would be. Here you got transmit data going out, receive data coming in, and then you need some way to clock this in. So you need to do something called clock recovery to figure out when you have a data stream coming in, you don't know when it starts or stops, and so you have to figure out when you're going to clock the data in. So there's a bunch of clocking logic for that. So part of the UART spec from the logic level is that there's a data frame. And it starts with a start bit. It has 8 bits afterwards. It has a parity bit and a stop bit. And some of these bits at the end are kind of negotiable. You pick. Maybe you don't want to have a parity bit. That's fine. Maybe you want to have 2 stop bits. That's fine. There are some versions of the protocol where you have 7 bits and some where you have 9 bits. But typically, it's 8 bits. You have a start bit, a stop bit, and a parity bit. Typically, now you have to decide if it's going to be how to interpret this data on your software side. Is it going to be most significant bit first, least significant bit first? You get to configure how many bits it is. Yeah, and you also have to agree on the transmission speed, so the baud rate. You have to agree, so the transmitter and receiver have to agree on all these factors in order to get communication to work back and forth. And these are just examples of other types of data frames. So one of the challenges here is you don't know when to latch in the data. Right? So we have a data stream coming through, and where are you going to put your clock edges? Or you don't, say another way, you have your clock edges here, but you don't know when the data is coming in. So now how do you choose when to clock in the data? If you clock it in wrong, you might clock on the edge. You might clock when there's no data coming in at all. So my question to you is, why don't you take, I don't have the prompt here, but why don't you take 60 seconds, talk to each other, figure out how you would make a microcontroller, figure out when to clock in the middle of the data packets to latch in the data into your shift register. How will you make that decision?
Just check, because your start bit is when you
It's a hard-coded protocol thing that like try to do it at this frequency.
wait just a little bit, so you're
Do you understand the question?
set the clock there or something.
There's like the first inside like how big your reading duty cycle is at.
Yeah, that you sync.
You're only reading it at when the data bit shifts like 0 to 1 or like 1 to 2.
Synchronization.
Models at or about somehow use the start to make
It helps with
And after that, clocks are synchronized. Yeah, basically.
The cycle hertz of the clock.
Anywhere. Anywhere. Let me see here.
Just looks like it's when it's
clocks per.
This prompted this question properly. So let me see if I can redo it a little bit better. Let's see. Do live puppetry here. All right. So here's my clock. This is my world that I live in. I'm a microcontroller. I have a clock coming by. We don't know when the data is going to be here, right? So like when the data is just flowing through in time, let's say, and like when do I apply those edges? If I apply it wrong, I might apply it like right at the crossing edge. That would be bad. But if I happen to choose this time when to clock in the data, this is good. Like my clock pulses fall right in the middle of the data, but you don't know what the phase relationship, you don't know when this start happens. So if you just start clocking in data, you don't know if you're hitting the middle, you don't know what's going to happen. And so there's, if you did no synchronization, if you did no strategy, there's likelihood you're going to get a bunch of errors. Does that help clarify the question? All right. Now we'll figure that out. Talk to each other and figure out the solution for me.
Wait, what is it common like a signal that's if the signal is high?
Yeah.
Right? You know that everything after this is like 8 bits of data. And then after 8 bits, wait for the word.
so like whether or not
I think what's going on over there.
Like you captures, you're able to post like live.
Right, that's kind of what I'm saying.
And like what if like interpreted the first bit of the data?
You know that
it should be a zero.
if you like
Well, he could yell at you. You could say,
Three data points for each data point.
if it's synchronous, that would work. Maybe have a baseball glove. He's not really good.
Well, it's either gonna, so like you could get 1.5 would be basically,
I think that's
if you go with majority. You could get.
I'm hungry
It probably won't be 3, it'll probably be like 30 next.
Just be like,
I think I'm gonna honestly run a peer pod or something.
I'll motivate the problem one more time. I'm learning how to do it. Don't worry. I'll get there eventually. Imagine you're pushing a kid on a swing. Your job is to push kids on swings. I spend a lot of my time doing this. That's why recurring problem. And so say you close your eyes and you just walk up, and now it's your job to perfectly push the kid in time. Or you got a bowling ball. So if I have my eyes closed, I don't know when to push. I have no idea. So I could push and the ball's like moving away. I'd miss. We use a synchronous method. When I push my kid, I keep my eyes open. And then I know right where the kid is and I can push them. So if you want to keep your eyes closed and push a kid, you need, how will you figure out when the kid is coming for you to push? Yes?
I think I got it.
Okay.
Is it you need to like first measure the first two to get the like the rhythm,
Okay.
and then like based on the first two, you can like guess the like how long the distance between the like the waves are.
I'd have to have some measurement method. So that's exactly right. Now, I will point out that the protocol gives you a little something. It gives you one start bit. So how can we use one start bit to figure out the phase or the timing at which I'm supposed to push the kid? It turns out you may, oh, good.
Say sample for the start bit.
Yeah, you can sample for the start bit. And there's probably some other piece of information that you know. Hey, stop it. Somebody's trying to break in? Well, I don't know how to deal with that. There's another piece of information that you actually do know. Here, do that. And then I'll do this. Which is you know what the time frame should be. So we didn't explicitly say it well enough, but there is a, go here. There is a baud rate, so you know the timing it should be. So that's one of the parameters. I should have set that up a little bit clearer. So you know how fast the data should be coming in, and so you just have to detect where that start bit is. And so to that point, here, what they do is they say, well, I know the baud rate, and I'm looking for the falling edge. That falling edge is the start bit. It can't be a 1. If the start bit was actually data, then there's a chance it could be 1, and then you wouldn't have a falling edge to time off of. So the start bit is always technically a 0. You could think about it that way, a falling edge, and then it just counts in to the middle of that time. And how does it do that? Well, it oversamples it. So in this particular example, we're using, let's see, I think we're doing 16, yeah, we're doing 16 times oversampling. So we're sampling much, much faster. We know that after the starting edge, it should be so many clock cycles. We know the timing, how long the bit, or the size of the bits. Then we know that 8 clock cycles in here is where the center of that bit will be. And then after that, we just go 16 clock cycles, 16 clock cycles, 16 clock cycles.
So if you like have like an STM with UART enabled or whatever.
Yep.
Is the RX and TX lines are just going to be held high, just like until something happens?
Yep. Yep. You're just waiting for that start bit to occur.
What if the D0 bit is 0?
What's that?
What if the D0 bit is 0?
But, that's fine. If the D0 bit is 0, then we've already recovered our timing. So I went up to the start bit. Start bit demands it must be a transition from high to low. I know how long approximately in terms of clock cycles that transmission should be, so you just count over 8 cycles, because we're saying we're doing 16 times oversampling. So now I go here, and then I just go 16 bits in the future is when I will clock this in. 16 bits in the future is when I'll clock the next one in. You could say it's, whatever this is, 24 or whatever as well. Does that make sense?
how do you know the mid bit is gonna be 8 clock cycles? Again, I missed that part. Or like, how do you know where the
Let's state it a different way. Let's choose some oversampling rate. You could choose just, you need to set up, you need to know when on this clock, when you should clock in data, okay? And so you can say, I have a falling edge. I know that I'm, say, much faster, a known number of clock cycles faster than the data coming in. In this case, I'm just going to wait until I'm that, and then there are microseconds over here, that number of clock cycles, and I'm going to clock in the data there. Does that make sense? So you can choose any oversampling technique you want. Typically, it's 8, 16, maybe 32.
Wait, what if the V0 bit is also a 0?
That's fine, then you just clock it in as 0.
Like, wouldn't the whole thing looks like a start bit?
But we know how long it's supposed to be, because we've pre-agreed, the transmitter and receiver have a pre-agreed on the baud rate or the symbol rate. Yeah.
How are you supposed to agree if you can't send data?
We have to go out of band. One programmer has to talk to the other programmer and says, I agree.
Oh, so like you read the data sheet and then you...
It might not be a data, yes, you read say you have a peripheral that only can talk at a certain data rate, but typically, like if you do this in lab, you have to tell your COM port on your computer, here's my baud rate. And if you choose the wrong baud rate, you get weird data coming in or no data coming in because you've misinterpreted where those clock edges are.
Peripheral has a baud rate that I have to set my data output to be at.
And you have to, and to read data in, you'd have to know what its baud rate is.
Okay.
Yep. So there's a priori information that has to happen for this.
Sorry, there's 2 baud rates?
Well, there's 2 directions of flow. There's one baud rate, sorry. And so for the other thing to understand, you must be on the correct baud rate, and for you to understand it, you must be on the correct baud rate. It's easiest, we've all agreed there's only one baud rate at a time.
Okay, makes sense. Thank you.
Yeah.
How is that, like, for certain devices constantly like automatically?
If you have enough, right, so if you have a nice computer that has lots of cycles and a little bit of logic, then you can figure out the baud rate. And so if you went and analyzed the data, you could figure out where the transitions are. So you might lose the first couple packets to when they do automatic baud rate detection. And so if we went and looked at like, let's see, is there an actual example anywhere in my slides? Let's look here, jump ahead. So here is an example of a transmission. We know that there should be transitions at certain time frames. And so if you just look at when you get transmissions, you can say, okay, probabilistically, this is the baud rate. Does that make sense? And even if the only problem would be if it was like all zeros, which would be a weird packet, and then you'd have like no data, or all ones. You'd only have the start bit. But usually you can figure it out through process elimination. What other questions are there? Okay. Now I realize I should have put in the baud rate beforehand, but baud rate is the number of symbol transitions that there are, which is different than the number of data bits that are gone through. So this is an example where the baud rate is 10 and the bits per second are 10. So say if this is a second, it just happens to work out where you'd have one symbol transition for every bit. Pretty good. Or every transition, there's one bit. Here's in a different example. This is binary, so this ones or zeros. And this has 4 different layers. We've made up a protocol. It's possible you could make this. Might not be practical, but you could make it. Where you have 4 different levels. And so now you can send, in each symbol transition, you can send one of 4 pieces of data. So now your data rate is much faster than your baud rate. That can happen. It can go slower too. You could have a protocol that has lots of overhead with it. Maybe you have to have addresses. Maybe you have to have control bits. And so now you could have a situation where just because you have symbol transitions does not mean that data is being transferred. So your baud rate can be below your bit rate.
Is baud rate only used for serial, or is it like, would that be a parallel?
Right. That's a good question. I see baud rate most used with UART, but the concept of symbol transition, so in RF world you call your symbol rate, which could be another version of your baud rate. So how often do your symbols change? That's just make sure the idea is that your symbols could change, which is independent of the data that's being transmitted. It's not always one-to-one. And the example of that is here, you have a start bit, a parity bit, and a stop bit. Those are transitions. Waveform is transitioning, but they do not carry any data. Information, yes, information about when to start, but your payload's only 8 bits, but you had to have 8, 9, 10, whatever, or 8, 9, 10, 11 transitions to get data across. So you have overhead associated with this protocol. Yeah. Parity is basically counts up either the number of ones or zeros, and if it's even, I think it's the number of ones. If the ones are even, then you get a 0. If it's odd, you get a 1. And so now you can do a parity check, which means, so the transmitter is going to send over and say, hey, I've sent over this many ones, and it's an odd number, let's say, and so my parity is 1. And then the receiver can come back and say, well, I've counted this many ones, and I look at my parity, and if it matches, your 50% chance the data is correct. Right? Which is way better than 0% chance, no method for detection, right? So, I mean, on the receiver side, I can go and say, like, is this packet corrupted? And it assumes only 1 bit would get changed at a time. If only 1 bit gets changed, this works. If 2 bits get changed opposite, then parity won't work. We have something else called CRC, so cyclic redundancy check, which uses more bits to encode the correctness of the data. And that's usually used in like RF protocols to ensure that the packets didn't get corrupted.
For the data frame, like if it could be 5, 6, 7, or 8 bits, like how do we know how many bits to read after the start?
You gotta. This is all a priori. You got everything on this thing. You have to decide beforehand.
Oh, okay.
You and you got to read the data sheet, or the other programmers got to agree. So. In this system, it's different than, like, say, Ethernet. Well, Ethernet, you still have to agree beforehand. There's a spec. But here, you're probably, you're making a PCB. You're making the entire system. So it's easy for you to know what it is. It's unlikely you're going to be in a situation where you have to discover what the baud rate is. It does happen when you're trying to get a microcontroller to talk to your computer, but then we have a human that can try all the different things, or automatic baud rate detection. All right. Yep. So just an example of baud rate versus parity bit. So if you have a baud rate of, say, 960 or 9600, each frame, and you've agreed beforehand that each frame has a start bit, 8 bits of data, a stop bit, and to say no parity bit in this particular version. You might be asked, calculate the actual transmission rate. What's the data rate? How much data can I put through this? And so the naive thing to do is to say, oh, there's my baud rate divided by 8, and there's my bits per second. But that, hey, why'd you, slides, naughty slide. Put slides there. But that doesn't work because you haven't taken account of those overheads. So here we have a start bit and a stop bit. So you have to subtract those off. Actually, so that equation doesn't work. Oh no, that equation does work. That equation works. But you basically have to account for the start bit and stop bits, and then that tells you how many bits per second you're actually making it through your thing. But the other thing that assumes that's your for the 8 bits that went across your UART, that would be the transmission rate. Except you can't utilize, it's unlikely you're going to be able to string packets, one packet after each other, and actually get throughput through that whole thing. So there's the idea of, like, how fast is the data going through? Yes, for one packet, but then if you put 1,000 packets through, there's space in between those packets. And that's going to, that dead time is defined by how fast your UART peripheral is pushing data out. And so if, just as a point to think about, if your project requires a certain bandwidth, a certain amount of data going through, just looking at the spec may not give it to you. So like BLE 4.0 and 5.0 say you get 2 megahertz of bandwidth. I mean, that's what theoretically the channel can take, but good luck actually getting that much data through that. Like, just practically, it's very hard to fill up the channel and have packets one right after each other in a way that can be received. So data rate for a packet is different than how much data you can get through reliably. Oh, here we go. Let's figure out what I said about parity was correct. So parity bit, see, even though we're at 1, it's even. Oh, so yeah, it is even if you count up all the ones, and I was right. If it is even, then you get odd parity. Okay, 5 bits. Yeah. So, well, maybe I was backwards. So if you get an odd number of ones, you get a 0. If you get an even number of ones, you get a 1 for parity. But that's the basic idea. Okay. So now you should be able to decipher what this is. You would go through, and a priori you'd have to figure out what the baud rate is, what the packet frame is, how many bits, how many start bits, stop bits, and parity bits. And then you could come in here and just say, okay, well, I see the start bit here, and I know how long it should take. And so from this edge to the middle, that's where the middle of the bit is. And then I'm going to go over 1 cycle to clock in the data. So I get a 1, 0, 1, 0, 0, 1, 1, 0, 0. You would already count up your 8 bits. You know that's a stop bit. Stop bit requires that you go back to 1 so that you can have a start bit. So this is an example where the 2 packets were put right next to each other, and then you could go forward. So by now you should, if you did all the calculations correct, be able to interpret that diagram. The trickiest part is figuring out exactly where the start bit is in that timing right there. Yeah.
How are you going to be figuring out which falling edge signals are start bit?
The start bit is always a falling edge.
Yeah, but there's falling edges, say, in the data bits. So how do we know which falling edge is start bit versus? We're
going to start in a world where the lines are high. Okay, let's just say it's been high for a while, at least multiple clocks, baud cycles. It gets pulled down low. This is the definition of, hey, this is a start bit. And then from here, I figure out my timing of when I'm going to sample in. And I already know how many bits they're going to be, because we agreed beforehand. So if there's 7, I know there's 7. If there's 8, in this case, there's 8. I know if there's a start or a stop bit. We agreed. So a stop bit. Therefore, this, I know that this should be the next transition, that this would be a start bit. That's the only thing it could be, because we've returned the bus back to its normal state, which is all high. Does that make sense?
Yep.
Okay.
What if it's the parity bit that gets corrupted?
Look, I don't know. What if the parity bit gets corrupted? Yeah, that would be a problem. So I think the other way to look at it is, what do you do when you found out there's an error? And so you, on top of this protocol, right, so this is like your Mac level protocol, you'd have to have another protocol that says, I have a corrupt bit, ask for it again, or ask for all the data again. So yes, that would still be a problem. If you were in a situation where you're really worried, you would use a fancier protocol, something like a CRC, that would give you more information about which bit got corrupted. Okay. Yeah.
What if the data is like 0.00001111? Will we just think the start and stop bit are just really long?
But you know that they're not really long, because you've agreed on the baud rate.
Oh, so we already know we're not doing blind, right?
Right, we're not doing that. Yeah. We're going to leave that exercise to, so a computer can do it because it can look up multiple packet transmissions, and it'll get the first one wrong, and it'll get the third one wrong, and you'll get a bunch wrong until it figures out the pattern. But we're assuming that we don't have the luxury of a full CPU. We want to get every packet, and that way we have to agree with the other person before what's the baud rate in the data frame.
Multiple peripherals from my microcontroller.
Yeah.
Do we take these lines high before we power the peripheral, or we power the peripheral before we take the line high, or does that not really matter?
That's a good question. I mean, I guess your peripheral probably has some startup protocol. And like all these edge startup conditions, it's usually if you just wait long enough, it'll reset itself because it knows like, so your error condition, I think you're saying is you have it low, you turn on your peripheral, it goes high, or it turns on, and then you raise the bus. And now it's like there's an edge, and now does that think it's data? Well, it doesn't have probably any of the other characteristics that it's looking for. And so, yeah, the first packet may be corrupted, maybe it doesn't matter, and then after a while it'll reset itself because it sees that there's no transitions happening. What do I want to teach here? All right, so here we have our transmit and receive registers. So shift registers are taking in data. So assume we are at the stage of clock recovery. And so now we have parallel data in here, and we can push it out to the, these are registers that hold the last transmission, right? So shift register shifted in, it's gonna get ready for the next thing. Here an ISR goes off that says I have new data, which means now you have to respond fast enough before the next packet gets in, or it'll get written over and you'll lose that data. So this is where ISRs come in or become valuable because they can respond quickly. Here, then you need to go and create a buffer, right, that will start holding this data, and that buffer would have to be large enough so that you know, your main program will eventually come around and get to the task of servicing this interrupt and making a decision servicing the buffer that you've created full of data and then doing some task with it. So a common problem in lab is students don't make that buffer large enough. You're like, well, I only got half my data or I got bad data. So just understanding this flow, there's a shift register you don't really have access to. When the shifting's done, it gets stored in the receive register, and then call an ISR that will store that somewhere until your main is ready. It's the typical workflow. Likewise, if you're trying to transmit multiple bits, you can go through and you get up, you send up, you create a buffer where you have your UART data to send out. When it sends, it can throw an interrupt saying, I'm done sending. In your interrupt, you can say, okay, take the next thing out of my buffer, put it into the peripheral, it'll send, and then it keeps waking up. So now you have a list of things that need to be sent. For what you guys will probably use this for is UART. It's kind of limited, right? It's only really good now for talking from one device to talking to another. And so it's like if you have a bunch of sensors on your chip, it's probably not the right serial protocol. We'll talk about other ones that are better. What it's typically used for is a way to talk to computers. So you have your UART, which talks, or microcontrollers will talk UART, and then it'll have a bridge. And that you have them, that's what you've been using on your device already if you've been talking through a serial terminal. But basically, you'll have a UART to USB interface. And USB is actually a pretty complicated protocol where it has negotiations back and forth about what the speeds are and those sorts of things. You don't want to deal with that. And it has a weird signaling thing where it has a differential pair, so it has a positive and negative version of the same data. So this chip takes care of it, and now you just send it commands, and it comes out onto your computer as a serial terminal. Makes it easy for a data transfer. So you'll find a bunch of those chips. A very common one is called FTDI chip. That's the name of the company. I've been doing this so long, I don't even know what it stands for. But if you just look up FTDI, you'll find these chips. It's a great way to talk to your computer. They also use this for Bluetooth, so you can get Bluetooth modules that are just UART. You just talk to your device through UART. This UART chip will negotiate that transfer to your iPhone or whatever your device is. You will have to configure this. There's a bunch of configuration data that has to be sent in, but they'll give you libraries. So now you can have a little embedded device. You don't even have to know Bluetooth, which is great. Bluetooth is painful. You don't want to learn about it. You just use a bridge. In lab, you'll use, if you want to do wireless communication, we have a bunch of Zigbee modules, or XBee modules, which is just a variant of Bluetooth, slightly different protocol, and now you will be able to make mesh networks. You'll be able to talk to multiple devices at once. You can have different channels so groups don't collide with each other. So that's like the easiest way to get wireless communication into your projects. Any questions? Yeah.
Just to make sure, UART you said is it parallel like communication and Bluetooth would be serial?
UART is serial.
Oh, is it? Oh,
Yeah.
yeah, that's right. Yeah, okay.
And you can, well, let's just say wireless is serial. It depends on the modulation scheme, but yeah.
If UART's serial, why in the early designs of it did it have like multiple different pins that you plug in? Like I saw it had like 8 pins.
Because I didn't go through it because it's boring, but you could have control pins and you could say, okay, are you ready? Yes, I'm ready. And especially when computers weren't fast enough, they had all these things to do flow control. And they also had muxes on them so you could direct data from one device to another device, and you had control pins for that. But we've deprecated all that stuff now. So your STM32, you have a lot of extra peripherals, right? You have 3 UARTs. I have never had a project with 3 UARTs. Matt just wanted to buy you, I think, the biggest nuclear the department would be willing to spend for it. So you got 3 UARTs, 3 multi-purpose UARTs, 2 normal UARTs, and then low power UARTs. I don't even know what those are. I don't know how they're low. It already seems really low power. I think basically you can be in sleep mode. Not a topic that we typically look at in this class. But you can put your microcontroller to sleep where you suspend operation, but it will still do UART operations, filling up buffers, doing those sorts of things. So when you do wake up, you have all the data there. Hey, it just stopped. It just said class is over. There's other, part of the multi-purpose UART port is that you can do other protocols other than UART with that same piece of hardware. So here, you can turn your UART into a IR LED remote, basically, and you can talk and transmit and receive IR LED or IR light as just an alternate method other than sending data through copper. Some of the pros and cons, so only 2 wires, which is great, except for that ground. You have to have ground wire or else you won't have a loop of current. Your things won't work. There's no clock necessary, and it has built into it, if you want to use a parity bit that allows for some error checking, which is nice. The downsides is that the data frames are pretty limited. You're talking about 8 bits per frame. Maybe you can do 9, depends on what your hardware supports, but it's not going to be like large chunks. It does not really allow for multiple peripherals or multiple devices to talk to. This is not the right protocol for that. It's just one chip talking to another chip. So you have the hardware has to do oversampling, so it's not really a con for you as a designer, but it's just important to think that there's an overhead because you have to do clock recovery. So that's why you need to do the oversampling. The other headache, as you've seen, is that you have to agree on the baud rate and data frame a priori. So beforehand, you have to know that or else it won't work. It's not something that you'd use for discovery. We didn't really talk about this. Maybe we should. So the internal clock has to be accurate and stable. And this is part of the problem if we go back. I have a few minutes. Oh, no. Come here. No. Oh, my gosh. Let's look here. Sure. If you get the timing of your start bit wrong, so say your clocks are slightly misaligned, and there's actually almost no way in the real world to get two clocks to be perfectly aligned. This is a big problem in wireless communication. So even though you set them to the same frequency, there's always some drift. So say your 2 clocks are slightly different, and maybe you didn't even make the best choice for your start bit midpoint. If you keep going, that error will start accumulating. And because the clocks are a little bit different, it could be that clock is out of spec, is out of the middle of the 9th or the 8th bit over here. And so this protocol allows for about a 10% clock shift, which is actually a lot, but we are in little microcontrollers. But this also kind of gives you a clue, because of this error here, is you have to recalibrate every single packet. Every time you have to do the start bit to figure out where you are, you can't retain that information to the next bit because you're going to accumulate error. If we go to this example, You could say, well, I figure out my timing here, I'll just keep using my timing all the way through. It will probably just work out. The problem is because there's skew between the two clocking devices, they're not on the same clock, and they're not perfectly the same, you may start accumulating enough errors to get these bits incorrectly. So every single time you have to go and recalculate the start bit. Thankfully, that's all done for you in hardware. You don't have to worry about that. All right. I'll end there, and come see me if you have any questions.
Transmission bursts. Yeah, I'm in the garage. Because you can very quickly recover the clock, only drop a few and then use the clock. I don't know how you do it.